Hey everyone, so I wanted to make a little screencast for you as you review for our little 2-question quiz that's coming up on stoichiometry. So I thought I'd start from the beginning and just go through what we can compare using a balanced chemical equation and how we apply that in a couple of different scenarios. So before you start this, make sure you have your periodic table handy and make sure you have a calculator and some paper as well. So let's get started. If you look at the example that I've provided here, we see a reaction between two different molecular elements reacting together to form one particular product. This is a reaction between hydrogen gas and nitrogen gas to make ammonia. Now, we know from our experience previously that we can take these visual models and communicate them symbolically. So I'm going to do that here and just translate this balanced reaction into a balanced chemical equation. And notice that for this reaction we have one nitrogen molecule, and the formula of nitrogen is N2, and it's a gas, and it's combining with three individual hydrogen gas molecules to form two molecules of ammonia. Ammonia is NH3. All of this is a gaseous reaction that's going on here. Now, the key thing to understand about stoichiometry is all about paying attention to this process and what it can tell us about a given mixture of reactants and how much products we might be able to form. Those are the common questions that we deal with. If I give you X amount of both reactants, how much of the products could actually form? And then we can get into more complex situations involving limiting reactants, but that's going to be the subject of my second screencast. So let's talk for a moment about what we can compare and what we can't using this equation. So what we can compare is we can look at this equation from a particle perspective. Okay, so we can compare it in terms of particles and say, well, for every one nitrogen molecule, 3 hydrogen molecules are required in order to form 2 ammonia molecules. So we can talk about it in terms of particles. Okay? This equation is also useful in terms of moles, where we can make a comparison of moles of one reactant to moles of another reactant. So we can say 1 mole of nitrogen gas will react with 3 moles of hydrogen gas to produce 2 moles of ammonia. Now, what we can't use directly is mass in grams. We can't say 1 gram of nitrogen reacts with 3 grams of hydrogen. It's simply not true. And the reason why it's not true is 1 gram of each material does not contain the same number of particles, whereas 1 mole, by definition, does contain the same fundamental number of particles. 1 mole of nitrogen gas is 6.02 times 10 to the 23rd nitrogen molecules. 1 mole of hydrogen gas is 6.02 times 10 to the 23rd hydrogen molecules. So we have to think about what we can use and what we can't use. So just to summarize, we can talk about it, this equation and the proportionality of the equation in terms of particles and in terms of moles, but we cannot talk about it in terms of mass in grams. Okay? So let's take this and let's apply it to a problem. So we're just going to carry on with our balanced equation here and look at a simple example where we're looking at a certain amount of nitrogen gas reacting with an excess amount of hydrogen gas, and we're going to figure out how many moles of ammonia can form. The first step in any of these problems is you have to write a balanced equation. So you saw me do it previously, but it's a good thing to always get in the habit of. So we're going to write a balanced equation as our starting point because this is fundamentally our recipe. This tells us the relationship between reactants and products in a given reaction. So NN2 plus 3H2 gives us 2 NH3s. Now, in terms of our strategy, the way we go about thinking about strategy has to do with what the question is asking. And in this question, it's asking us to solve for moles of ammonia, and we're starting with moles of nitrogen gas. So in this case, what we have to recognize is we're starting with moles of N2. And we have to convert that into moles of NH3. So our strategy is to go from moles of one substance into moles of another. And the way that we'll do that is by using something called a mole ratio. So for this particular problem, we need to compare the mole ratio between nitrogen gas and ammonia. And notice from the balanced equation, that's a 1:2 ratio. So here's what the solution looks like for us. We always start with the given value, the measured value. And so for this problem, it's 2.5 moles of nitrogen gas. Then we use factor label method to set up our proportion, where we use the mole ratio from the equation that you see I've underlined here in red. For every 1 mole of nitrogen gas, I produce 2 moles of ammonia. Now some quick math, and I should get 5.0 moles of ammonia gas produced. You know you set up the problems correctly if your factor label method always cancels out the unit label you don't want, and you're left with the unit label that you do. So that was the simplest example where our strategy just involves one single conversion. And the way that we'll know how many steps we have to deal with is really how many arrows we've drawn in our strategy. So let's look at one that's a little more involved. So we're going to just stick with the same equation. So again, start by writing a balanced equation. And not all problems will have visual models for you up above, so you're going to have to use your skills in writing chemical equations to be able to get started with many problems in stoichiometry. And then let's do a little quick analysis. What are we really dealing with here? Now, the problem's different. This time we're solving for grams of ammonia given grams of hydrogen gas. So our strategy has to change as a result of that. So what we're going to do in this case, our strategy has to be, well, first, we can't compare grams directly to grams. Remember, that's a fundamental comparison that will not hold true using the proportion from our equation. So it's easiest to convert things into moles. Just think of the common currency of stoichiometry is going to be converting reactants or products into moles and then making a comparison using the balanced equation. So for us, we have to first go from grams of hydrogen into moles of hydrogen. That's our first step. And we can just use the molar mass for that conversion. And then we're going to have a second step. The second step will be from moles of hydrogen to convert into moles of ammonia. And we're still not done yet because notice the problem asks for a mass of ammonia in grams. And the final step needs to be we go from moles of ammonia into grams of ammonia. So if you look in our strategy in red, we've got 3 arrows, which means our solution is going to have 3 steps. So let's set this up using factor label method. Always start with the measured value. So our measured value is 12.0 grams of hydrogen. And then the next step, use a molar mass. And the molar mass for hydrogen, remember it's diatomic. So its molar mass is 2 grams per mole of hydrogen gas. And then that takes care of that first step. So we use the molar mass to go from grams of hydrogen to moles of hydrogen. Now to convert from moles of hydrogen to moles of ammonia, that's where we need to use our ratio from the balanced chemical equation, which in this case it's a 2:3 ratio. So we make that so that hydrogen moles cancels out. So that's 3 moles of hydrogen and 2 moles of ammonia. That takes care of the second step. And then our third step is to convert between moles of ammonia and grams of ammonia. So we can set it up like this. 1 mole of ammonia. And then we have to calculate the molar mass of ammonia. So this is where your periodic table comes in handy. Look up your atomic mass of nitrogen and then add it to 3 hydrogens. So that ends up being a molar mass of 17. If we look before we do any calculations and cancel out our labels, everything cancels away. And then we can do our mathematics. And we'll see, let's see, 12 over 2, that's 6. 6 times 2, that's 12 divided by 3, that's 4. So we have 4 times 17. So that's like 68. 68 grams of ammonia. Okay. Now, use this problem and the strategies that we've done with the previous two problems to try one on your own. So take a look at this problem right here. This is a problem that was first introduced to you in the Pogel on stoichiometry. It was on the very first page. So I want you to pause the video right now, and then I want you to fill out the balanced equation, the strategy, and then solve. And in a moment, you could unpause the video and then reveal and check your work with what you see on the screen. So pause your video right now, balance the equation, write out a strategy, and then write out your solution. Okay, so hopefully you've had a chance to do all of the strategies that we've demonstrated in the past two examples. So let's take a look and check your work. So let's first start with the balanced equation. Now, if you didn't notice before, you should have seen that up in the upper part of the slide, there was a visual model of the reaction that happens between between acetylene, which is C2H2, and oxygen gas to make CO2 and H2O. Now remember that combustion always requires oxygen as a reactant, and if the fuel is a hydrocarbon, you're going to produce carbon dioxide and water as products. So the balanced equation is 2C2H2 plus 5O2 yields 4 carbon dioxide molecules and 2 water molecules. Now the strategy that we should have identified is from our analysis of the problem. Notice we're solving for grams of acetylene, which is C2H2, and we are given a measured value of water that we want to produce, in this case 36 grams. So our strategy becomes we start with our mass of water that we want to produce, we convert that to moles. Remember, the common currency of stoichiometry is to convert things into moles. Once we have it in moles of water, then we can use the mole ratio from the equation in blue to convert it into moles of acetylene, that's C2H2, and then use the molar mass of acetylene to get our answer into grams of acetylene. And the work for that looks just like what you see down below. Notice if we do a quick unit analysis, we start with our mass, our measured mass of water, and we convert that into moles using the molar mass of water, which is 18. We then convert from moles of water into moles of acetylene using the mole ratio, because the ratio in question is 2 to 2. And then we convert from moles of acetylene into mass of acetylene using the molar mass of acetylene, which is 26 grams. And our final answer, which we should give to 3 significant figures, 52.0 grams of acetylene. So that's a start for us. The next screencast will be on limiting reactants. Hope you found this one helpful.